All right, next is Alex Atkinson from Florida State University.
A couple videos on video.
Okay, cool.
Here.
Thank you.
Okay, hey, how's it going? My name is Alex Atkinson. I'm here at FSU through Austin, Mass, and collaborating on this with Barbara Costa and Alex Leeds, who's doing a lot of the kind of back-end development on some of this stuff. So I'm focusing on 3D Gaussian splatting and neural radiance fields and surface reconstruction from those algorithms. And it's building off of previous research into photogrammetry where we were trying to capture specimen in the field. And we found that you can efficiently do that, but it kind of caps out at certain levels of complexity per specimen, like these delphinium here. You can see there's kind of some data loss or like additional kind of warping, as we've seen with photogrammetry. I'm sure you're very familiar with this. And then specimen like that dandelion on top are just like kind of altogether impossible due to the nature of photogrammetry. But with these new algorithms.
Yeah, did you see
Oh,
it
shoot.
says, yeah.
No. Two-factor.
We've all been there.
All right. So as you can see, these algorithms are able to accurately reconstruct even these extremely fine filaments of a dandelion. So kind of an exciting development there. Perhaps it could resurrect dead data sets because of this.
I think click the top tab up in the browser. Yep, there you go. Oh,
Okay.
no,
No,
that's
hang on.
not in the right place. Yep.
There we go. Okay. Yeah, so what's happening here? It's able to take missing data that can be inferred through sort of like secondary sources. So you're taking photographic input, RGB, it can be video as well, and then it's running it through traditional computer graphics algorithms like ray tracing and sort of these other typically non-photo reconstruction algorithms, and then applying those with neural networks to photographs to be able to reconstruct lighting scenes and information from that by pixel density or surface information of objects or scenes. Okay, so here's a breakdown of the pipeline that we've been running so far. All of this is built on photogrammetric architecture, which is really nice. It's all open source. Very emergent, and a lot of sharing of these algorithms and a bunch of different techniques. So this is just one possible pipeline. So you take kind of that first step of matching and feature extraction from photogrammetry, and then you're applying that to then either the neural radiance field or 3D Gaussian splatting algorithms, which take up those structure for motion points, and then run that through a different rasterization process, either the neural radiance field or the Gaussians. And then run that through a neural network, which is refitting the lighting information, pixel density, depth of field, things like that, from back to the images and continuously refitting that. And then it does a very similar process to also gain a mesh that you can extract from these. And again, there's many kind of interoperable pipelines where you could use various algorithms within that. Obviously, everybody seems pretty familiar with photogrammetry, so I guess I won't really backtrack on that too much, but this is the data, the first kind of step that you're taking, those camera positions, and then your sparse cloud information. And then what happens, so this is where things get a little, thank you, a little bit different. So in the case of, on this one here, this is the neural radiance field. So you can see it's then extrapolating out many projected rays of light and essentially kind of bouncing them off of the objects or other things in the scene, the entire data of the scene, and then refitting that again against those images. The 3D Gaussian method is a little bit different. It's fitting an array of these Gaussian distributions of pixels. So they've got pixel density and color data on that Gaussian distribution, and they kind of stack those in like harmonic spheres and then map those to a depth map. Maybe, yeah, there we go, cool. So here's, just a further breakdown of what that looks like. You rasterize, you go through the neural network, it fits it to the images and then recreates a scene based on that. And here's just a couple examples of the differences. So this one here is, these are pretty low resolution, so kind of to emphasize some of the information in the scene. This is a neural radiance field. You can see it looks very sort of pixelized. These are actually voxels, so they're 3D pixels, a little bit more data there. And these are all running on my 4060 Ti graphics card, which has 16 gigabytes of RAM. This is a Gaussian splat, and you can see that it's kind of hard to tell here from this low res, but there is a little bit more information and accuracy from the Gaussian method, and it tends to be somewhat significantly more computationally efficient. So that is why we kind of decided to focus on that side of things. And then we were also able to find out that you're able to get decently accurate. We need to further test this, but so far we're down to about 100th of a millimeter across different points of a mesh that's been extracted from that. And this is, I think, maybe a pretty exciting moment. So this is a head-to-head comparison against photogrammetry using Metashape. Exact same data set, untextured mesh here, using downsampled images to 720 pixels. And you can see that there's a lot more detail on that mesh from the exact same data set. This moment right here, this kind of broken occipital arch, is something that, I wanted to make sure was kind of in the data set. It was kind of our focal point. And so here's a 6K resolution image from a mirrorless DSLR. And here's an untextured Metashape mesh from those 6K images. So this is like very high res. And you can see it still fuses that arch. So it's kind of exciting that we're able to get on the 720 data set, it's able to maintain that geometric accuracy. Here is a hybrid render. These are kind of like real-time renders, so they're sort of weird. The texture is applied through real-time rendering. So it's a little bit different method, but that's what that looks like. This is, again, downsampled to 2K because now we're using Amazon Workstation Cloud GPU, and we already capped out our 24 gigabyte VRAM at 2K. So that's what that looks like. And there's a lot of headroom there for that, using better GPU systems and things like that. So also kind of exciting. There's a 6K Metashape fully textured mesh. So as we've seen, photogrammetry, especially on optics like this, can produce amazing results. But that's the head-to-head against our 2K render. So getting pretty comparable even on the textured mesh. And again, maybe maintaining some better geometric accuracy. And here's just what that full, here's what that full render looks like in the real-time render view. Pretty comparable to photogrammetry, even at those lower resolution scales. So, okay, so next steps, we want to kind of test this up against things more traditional measurement methods like a microscribe, perhaps. We're hoping that this opens the door to interspecies study, like amongst a population where you might need a lot of data sets to have this opens the door to sort of more rapid capture. As you can see, you can have a more incomplete data set and lower resolution images. So it's a lot more efficient and can use more incomplete data sets or fewer images to get, in theory, a higher quality reconstruction of that model. We want to look into how far we can push that kind of next. And just a few other takeaways from these methods is they're really good at capturing like surface reflectance because they are like light-based reconstruction methods, and these extremely fine, like the filaments of this azalea here. That image or that model was captured in the field. That flower was moving around. That was my cell phone captured that, and it was still able to get those filaments. So again, it really kind of opens the door to some other conditions of being able to model out in the field with like pretty decent accuracy, even in much less than ideal conditions. Again, it's very, very efficient in terms of the data sets. You do have to kind of outsource then your upfront costs of maybe like doing all these really elaborate photogrammetry methods. You do have to have a really nice GPU, but the capture method might be a lot more efficient. It could potentially resurrect some dead data sets because it's able to get things out of it that the previous methods weren't. Again, that unconstrained capture, and it is so far we've proven down to 100th of a millimeter accuracy. Yeah, just some acknowledgements there. Thank you.
Now know how we're going to do the fish guns.
Yeah, right.